Everybody, let's get started. So I'm very happy to introduce Andrej, who's one of the program organizers, and also another longtime Simon's advertiser. And he did his PhD with Sanjeev Aurora at Princeton, and he was a postdoc at MIT. Now he's faculty at CMU. And you can look him up and you see them for awards and a bunch of standard good stuff. A few anecdotes I want to share is that, of course, as implied by the photo, we're very eager to be here and getting a lot of work done. These are all things you can look up, but I want to highlight one thing about his personality, which is always hard to identify for young faculty, which is he's already a very accomplished advisor. So amongst the research fellows who already have superstar students of his, even though maybe guess that he looks like a student still. So
credit goes out to the students.
Yes, very good. It's like the good advisor. So, my point.
Thanks, Matus. In fact, I actually met Matus during one of the earliest, what was it called, theory of deep learning or theory of machine learning programs? Yeah, what was the 2017? Deep learning? Yeah, so that's where we met, actually. Okay, cool. So I'm going to tell you today a little bit about some statistical properties of score-based losses, which is a kind of emerging kind of way to fit various types of generative models. This is kind of going to be a survey-style talk of a bunch of works. And just to kind of ease us off a little bit into the topic, unless you've sort of been living under a rock, generative models is like an area of AI that has made kind of very big strides in the last decade. So about maybe 2014, GANs came out, and we were all kind of very impressed with these little tricks that you could do with them, like style transfer, so it kind of make the Mona Lisa look like it was painted by Van Gogh, or put Nicolas Cage in your favorite movie. And then around 2021, the kind of first version of DALL-E came out, and again we were all kind of super impressed that you could get the model to generate some pretty kind of strange things. So you could kind of ask DALL-E to generate an armchair in the shape of an avocado. It could kind of reasonably comply. And nowadays, I generated this for the occasion. You can even kind of get these models to generate some pretty sensible pictures corresponding to some pretty weird prompts, like Abraham Lincoln taking a selfie on the Golden Gate Bridge. I did try to do something more Berkeley specific, but it just wasn't coming out very nicely. So sorry, it's more SF specific. Okay, so I'm going to look at sort of one basic task in this distribution learning pipeline, which is kind of something that I'm sure most of us are familiar with. So kind of one of the basic ingredients in generative modeling is the following sort of, I guess, task. So you're given a bunch of training data, that's x1 through xn, IID from some ground truth distribution p star, let's say pictures of puppies. Then there's some kind of learning procedure where what you do is you kind of commit to some parametric class of distributions p theta, and you some ways try to pick out the best parameter theta in this kind of class of distributions. This gets you some guess p theta hat for the distribution, and then the way that you're going to use this model is, if you want to generate further examples, you're going to try to draw samples from this distribution, and what you're really hoping for is that these kind of samples look like something from this ground truth distribution p star, so kind of pictures of new puppies. The way you can kind of operationalize kind of both parts of this pipeline is varied. In terms of the learning part of the pipeline, perhaps the most kind of standard thing to do is, as Matus had in his talk, is maximum likelihood. So this is kind of just trying to, your kind of best guess for the parameters is the kind of parameters theta that maximize the sum of the log likelihoods of your training data. And to give this a name, I'm going to call this theta hat MLE for maximum likelihood estimator. There's kind of good reasons from classical statistics for why this is a sort of de facto choice for an estimator. It's not going to be super relevant for the talk, but kind of very roughly in some asymptotic sense. So if you let the number of samples go to infinity, this is going to give you the best sort of expected L2 squared error of the estimate theta hat to the kind of best parameters theta star. So that's why we like this. The reason why we don't like it is that oftentimes optimizing this objective can be intractable, and I don't really just mean intractable in the sense that it's non-convex or something. That's a kind of common thing. Even running a kind of gradient-based method can be challenging to do. So let me give you one kind of case study where this happens. Oh. Yeah, yes, please heckle away.
Why do I care about the parameter?
You can heckle about that for sure. So it's because it's the only thing that I know how to analyze. It's kind of classical that the easiest version of the problem if you're trying to analyze statistical efficiency is going to be parameter learning. Then next over is kind of improper learning. So you want to be close to the distribution in some distributional sense. I just don't know how to say anything about this question. And as you'll see, even the parameter learning version was open before this work. So yeah, but that's a very reasonable heckle. Any other heckles so far? All right, good. So let me kind of give you a case study for how these kind of difficulties with the maximum likelihood manifest. So I'm going to talk about what's called the energy-based modeling paradigm. So this is kind of relatively natural. So the kind of in this case, the kind of class of probability distribution that you're going to care about has the following form. So it's going to be parameterized up to some constant of proportionality. So p theta of x is going to be proportional to the exponential of some energy function e theta of x. And typically, this energy function is such that you can do some nice things with it. So maybe you can evaluate it easily. You can take gradients of it easily, and so on and so forth. So again, sort of pros and cons. Why is this a kind of nice class of probability distribution? It's kind of nice because it's very flexible. You can take the class of energy functions e theta to be just about anything you like. So for example, maybe you can think of e theta as being a neural network where the theta is parameterized the weights of the network. OK, so what do we not like? Suppose that you want to try to draw samples from this distribution. Well, this sort of class doesn't really seem to come with a natural sampling algorithm. So the typical thing that you try to do is you try to run some kind of Markov chain. I'll show you some examples of Markov chains that are common choices. In fact, if you try to train it with maximum likelihood, so if you try to just optimize the likelihood, even kind of running a first-order gradient method seems to be kind of challenging. So the reason for this is basically the following. Let's see, do I have a pointer here? I guess I have a pointer here. So if you try to write down, for instance, the expression for the gradient of the log likelihood of a data point, well, you can kind of plug in the expression for up above, and what you're going to see is that there's the gradient of the energy function. Typically, this is going to be something easy to do. If it's a neural network, this is just back propagation. But there's this additional term, which is the gradient of the log partition function. And if you kind of rewrite this expression, what you can see by chain rule is that this is 1 over the partition function, the gradient of the partition function. And this is just the expectation under your current guess of the parameters p theta of the gradient of the energy function. And there's really no kind of straightforward way to do this other than try to draw samples from p theta, which you will typically do with a Markov chain, and then estimate this expectation in a Monte Carlo fashion. The reason this is going to be challenging is the same reason sampling is challenging. The mixing time for whatever Markov chain you pick can frequently be very, very bad. OK, so energy-based models have a kind of very long history in sort of generative models and machine learning more generally. Arguably, the very first generative models that actually worked at all were kind of energy-based models, which took inspirations from graphical models. So restricted Boltzmann machines are a type of easing model, which were kind of arguably the first generative models that worked at all. The way you train these models is actually using the recipe that I had on the previous slide. So what you do is you try to kind of optimize the likelihood using some first-order method. And the Markov chain that you use is something called a Gibbs sampler. And kind of if you merge these two together, this is commonly called contrastive divergence. It turns out that using kind of neural net parameterized functions somehow didn't work until relatively late. Again, arguably the first kind of paper that made this work at all was this very nice paper by Du and Mordech in 2019. And again, the recipe that they use in this paper is kind of what I had on the previous slide. So you do maximum likelihood, you try to do gradient descent, and you use another Markov chain. It turns out for continuous distribution, a natural Markov chain is what's called Langevin, and I'll come back to that in a few slides. What happened around the same time with the seminal paper by Song and Herman is that people kind of started thinking about abandoning doing maximum likelihood altogether and instead trying to just fit the parameters using some alternate losses. So score matching is one of these losses that I'm going to spend quite a bit talking about today. There were other kind of proposals at the time. So noise contrastive estimation is another one. And somehow, even though these methods kind of had a long history, in fact, score matching was Depends how you actually want to trace out the history, but dates at least as far back as the paper by Hyvarinen in the early 2000s. And then sort of people took these losses and kind of applied various types of annealing strategies to them and took them to some continuous limit. And this kind of gave rise ultimately to diffusion models, which are basically the kind of dominant paradigm in generative modeling for images. So as I said, the talk today is going to be focusing on these kind of score-like objectives, and I'll tell you kind of what precisely I mean by these objectives. But maybe this is a good sort of pausing point to see if there's any heckling or questions. Okay. No heckles, no questions. Good. All right, so let me kind of walk you through the basics of score matching. So here's sort of the very rough idea. So, okay, the problem somehow with maximum likelihood in energy-based modeling was the fact that we have this partition function. So the idea is, why don't I, instead of maximizing the likelihood, try to kind of match what's called the score of the distribution. So the score of the distribution is the gradient with respect to the input of the log probability. This is a vector field. So at any point, x is going to give you a vector, and it's basically giving you the direction in which the kind of the probability mass is increasing. And what I'm going to try to do is I'm going to try to match this function in the L2 sense. I'm going to try to find the parameters theta that sort of try to minimize the expectation under p data of how far away these two score functions are. Okay, so how does this help? Okay, if you write out the expression for the gradient of the log probability, because the partition function doesn't depend on the input, it doesn't show up anymore. So it seems like one of our problems has been resolved, so we don't need to kind of calculate the partition function. But there's kind of another sort of obvious issue with trying to fit this objective, which is what? Yeah, exactly. So log p data is not known. So if you just want to kind of evaluate the score at a particular training data point, you don't actually have that. The only thing that you have is samples from p data. So we kind of have to deal with that. So the kind of strategy that was proposed in this paper by Hyvarinen is to sort of make a clever usage of the integration by parts. And sometimes this goes into literature by implicit score matching. So here's the idea. So you're going to take this objective that we're working with, so this expectation of the difference between two quantities squared. And what I'm going to do is first I'm going to kind of expand out the square. So you see I'll get three terms, right? I'm going to get the expectation under p data of grad log p theta squared, then expectation under p data of grad log p data squared, and then this kind of cross term between grad log p theta and grad log p data. And so now what I'm going to sort of observe is that if I look at this objective, the first term is fine. It's an expectation under p data of a quantity that only depends on p theta, so I can turn it into an empirical counterpart. The second one I just don't care about because it doesn't depend on p theta at all. So sort of the only thing that I still have to care about is this cross term here. And it basically turns out that if you do integration by parts and under some sensible assumptions about decay at infinity, what you can do is you can kind of move one derivative from p theta to p data, and you can sort of see that this kind of cross term is equal to the expectation under p data of the trace of the Hessian of log p theta. And so now I'm happy. So now this means that this objective I can equivalently rewrite as kind of things that look like expectation under p data of quantities that only involve p theta. So I can kind of turn this into an empirical objective that I can try to train. So then what I'm going to do is if I have some finite number of training samples, I'm going to look at the following estimator. I'm going to give it a name. I'm going to call it theta hat SM for score matching. So it's just going to be minimizing the kind of empirical counterpart of the above expression. So it's just the kind of average over the training points of the same expression. So as I said, this sort of objective was first proposed in this kind of early 2000s paper by Hyvarinen, and basically he showed that under some kind of technical conditions, this estimator is consistent. What we're going to be talking about today is more about kind of more fine-grained statistical properties of this estimator. Okay, so a bit more of preamble. So okay, this. So now suppose that you're good at this task. So somehow suppose that you manage to estimate the score of the distribution reasonably. Now you kind of might wonder how do you actually kind of use the model inference. So how do you draw new samples? Well, unfortunately, now you still have to run a Markov chain. But the kind of good thing is now you only have to do it at inference time, which is to say to produce new samples after the model has been trained. You don't have to do it at training time. Okay, so what is the Markov chain that you're going to use? So this is kind of a version of what's called Langevin diffusion or Langevin dynamics. So basically, in a nutshell, what you want is the following. So there's some distribution P of x, which is proportional to exp of e theta of x. So it's kind of parameterized up to a constant of proportionality. And what you want is some Markov chain that kind of produces samples from this distribution. The idea behind the Markov chain is basically it's a kind of cousin of gradient descent. So what you're going to do is the following procedure. If you're at some point xt, what you're going to do is you're first going to move in the direction opposite of the gradient of the energy function. So that's like a gradient descent step. And then you're going to inject some appropriately scaled amount of Gaussian noise. So you're going to sample some zeta from a standard Gaussian and then multiply it by square root 2 eta. And then it turns out that if you sort of take the limits in some appropriate sense, the kind of limiting object, you can think of it as a kind of stochastic counterpart of gradient flow. The kind of limiting object is a stochastic differential equation, which is called Langevin diffusion, which basically looks like the following. So kind of infinitesimally, if you're at some point xt, you move in a direction opposite of the gradient of the energy function, and then you inject Brownian noise. And the kind of basic property of this stochastic process is that if you run it kind of very long, the equilibrium or the stationary distribution is the target distribution that you're trying to draw samples from. So if you run this process for long enough, you kind of hope that it's going to generate samples from something close to your desired distribution. So what that means is that, if you have some estimate of the score, what you can do is you can run the following you can kind of run this Langevin procedure. So you can basically move in the direction of the estimated score, inject a bit of Brownian motion in the continuous case, or Gaussian noise in the discretized case, and then you kind of hope that if the score was estimated well enough, then this process is going to converge to something close to the data distribution. I should note that even this kind of thing that's a sort of, I guess, footnote here for me, which is if you manage to estimate the score, then this process will converge to something like the data distribution. Actually doing the kind of numerical error propagation carefully and precisely is like a kind of nice, rich direction in the literature that has been developing in the kind of last couple of years, starting with a paper by Adam Block et al. And it's a kind of subject to another talk, but this is also kind of a very interesting direction, kind of the theory of diffusion models in the last few years. And sort of the way that this will look pictorially is the following, right? So you start with just noise, and then you run this Markov chain, and then eventually, as you keep running it, it's kind of converges to something that looks like samples from the distribution. Okay, so this was all kind of preamble. Oh, sorry, go ahead. Error propagation rates. There are a bunch of rates for a bunch of different types of kind of both stochastic models and deterministic sort of models. So I guess if you know the literature, kind of OD-based and SD-based models. Talk to me afterwards. There's sort of open questions there as well, but it's going to take me a little bit too orthogonal to this. But yeah. Say that again. X which? Yeah, that's depends if you're asking me theoretically or practically. Practically, there's usually a bunch of tricks for how this gets done, kind of buffering strategies, warm storming strategies. But the most, I guess, standard thing to do is just like a standard Gaussian or something else, uninformative.
Can you repeat the question?
What is x0? Where do you initialize when you're trying to do the sampling? Okay. So let me actually tell you now what we're going to be asking today. Maybe some of you already imputed, but somehow these kinds, as I said, these kind of estimators, though they were kind of proposed a while ago, their kind of statistical behavior wasn't really understood. So kind of the question that we're going to be asking is, what is the kind of the statistical cost of switching from maximum likelihood to score matching? So what I mean by this is there was sort of a reason that we switched from maximum likelihood to score matching. It was this kind of idea that we get some kind of algorithmic benefit from it. So we avoid calculating the partition function. The question is, what did we sacrifice in this trade? So we kind of know that maximum likelihood is sort of the gold standard statistically that kind of we're comparing to. And again, I'm not going to sort of state anything very formal here because there's a variety of results and they're all kind of quite technical. If you want a buzzword for a theorem to look up, you can look at the Hayek-Lecombe theorem, or you can open your favorite textbook on kind of asymptotic statistics, for example, Wonderwort. But sort of roughly what you want to think of is that among all kind of nice enough estimators theta had, maximum likelihood is going to give you the smallest expected L2 squared error from the kind of best parameter theta star. star. And that's sort of the thing to keep in your mind. So this is kind of the sense in which it's a gold standard. And so now we just want to ask, how much worse is score matching? That's the question. Everybody with me? Yes.
Some slides ago, you did say someone did manage to implement MLE with using the sample.
Yeah.
Like a heroic feat that they did this in.
So the answer is it's quite tricky. So basically what you have to do is when you're doing maximum likelihood, when you're doing the sampling to estimate in a Monte Carlo fashion, these expectation of the gradient terms, you have to be kind of careful with where you warm start the chain. So what they do is basically they kind of keep a buffer of past iterations, and then they mix with some magic proportions the amount of buffered samples and the amount of just fresh Gaussian sort of noise samples, and it somehow works out. There's a bunch of kind of magic ingredients in the kind of empirical recipe. It's also not entirely clear if there's some qualitative differences between the kind of final converged model. Again, there's sort of some empirical evidence that there's some weaknesses with either approach, but maybe talk to me offline and I can tell you a bit more. Yeah. Yes?
Can you make any assumption on P data? For example, P data is generated by some fraction followed by the star.
So far, I haven't done that. In what I'm going to say next, I will, because I'm going to be talking about parameter estimation. So it better be the case that there's at least it's going to be sort of P data is equal to P theta star for some theta stars in a moment. Yeah.
Can you just say a little bit about the consistency result of environment first?
It's going to maybe let me go because I have to set up a little bit more, and then we can maybe go back. Yeah. Okay. Good. So now let me kind of tell you. So we'll proceed in several parts. So first, I'm going to kind of tell you about the basic framework that we developed in this kind of paper with Xander Hackett and Fred Kohler. Xander was actually a rising junior at the time, so this is something to make us all feel worse about ourselves. So the starting point is the following. So in this kind of paper by Song and Herman, what they noticed is the following. So they noticed that if you look at kind of distributions that look kind of bimodal, so perhaps like a mixture of two Gaussians, one in the bottom left corner, one in the top right, you kind of expect that maybe the kind of estimate of the score is going to be good closer to where there's a lot of mass, so kind of closer to the modes, and kind of to be bad where there isn't a lot of mass, because in the empirical counterpart, there are no points there. And so somehow you worry that this is going to cause issues with the distribution that you've estimated. In 1D, you can actually check how severe these issues are. So what you can do is, in 1D, you have fundamental theorem of calculus. So once they give you a score, you can extrapolate it into a density. So you can check if I have, let's say, a mixture of two Gaussians, and I vary the separation between the two components in the Gaussians. You can try to check how much worse maximum likelihood is compared to score matching. And what you can see is that if you make the kind of modes further and further apart, the kind of, maximum likelihood and score matching will diverge. Then score matching is going to start getting worse and worse. Whereas if the kind of the separation is not too bad, they're basically on top of each other, which is the left picture. So fine, but kind of multimodality is one of these, common high-dimensional boogeymen that sort of everybody knows that kind of cause problems for basically any method you throw at it. There's kind of other reasons why you might have these like low mass kind of parts of the distribution. Maybe distribution is supported on some lower dimensional manifold. Who knows? It's kind of hard to pick out what is a generic sort of phenomenon, what is a good general principle that causes this. Yeah, go ahead. Correct, but at finite number of samples. So this is you're running maximum likelihood. Yes. There's going to be no optimization what I'll talk about today. It's all going to be about statistics. Yeah. Okay. So here's so before I tell you the result, let me first tell you what the message of the result is going to be, because I have to kind of give you a couple of technical preliminaries. So the summary is going to be the following. There's somehow going to be a very nice and surprising connection between the computational efficiency of the algorithm that you use the score with to generate new samples. So these Langevin dynamics, and the statistical efficiency of the kind of the score matching, which is the kind of the method by which you're fitting the distribution. So roughly speaking, the theorem is going to have the following form. So if you kind of want to look at the error of the score matching estimator, so theta hat SM minus theta star, you can upper bound it by the error of the maximum likelihood estimator times some quantity that has something to do with the mixing time of Langevin. and then times some quantity that has some kind of nuisance quantity that has something to do with how nice and smooth the score is. And I'll tell you sort of what the results look like in the asymptotic regime. So this can be for some sufficiently large number of samples. Why is this nice? It's nice because it's in some sense telling you that you should expect this method to be sample efficient when the way that you're going to use the kind of estimated object is algorithmically efficient. Why is it surprising? It's surprising because a priori it doesn't really seem like kind of the sampling algorithm, which is to say kind of how you use the estimated score, doesn't seem to have anything to do with kind of how you're fitting it, which is the score matching. So it's kind of aesthetically pleasing and somewhat surprising. So I'll tell you kind of what's the formal version of this once I kind of give you a little bit more technical preliminaries, but maybe kind of, are there any high-level questions before I start doing that? Okay. Oh, sorry, go ahead.
So what are you going to be assuming about the class of distributions?
Warm-up example. So let's first look at the case of exponential families. So in this case, the parametric family that I'm going to be looking at is p theta of x is proportional to x of theta inner product f of x for some chosen what are called sufficient statistics f of x. So like a kind of example here might imagine is if f of x is, for example, the kind of first and second order moments, then this is just kind of the standard Gaussian. You can think of this as some kind of like, energy-based analog of a kernel. So you can think of this f as a kind of feature map, and you can think of the thetas that you're fitting as weights over these feature maps. So this is some kind of distributional analog of what we think of as simple cases in kind of in just sort of like supervised learning. So some kind of like fixed feature example. So even though the setting kind of looks simple, in fact, if you try to, for example, fit the parameters theta for an exponential family with maximum likelihood, it's not actually clear the fact that this distribution kind of family looks somewhat simple. It's not actually clear that it makes sampling any easier. And in fact, it doesn't. So as I'll show you, even in this very simple family, if you pick f to be, let's say, like, bounded degree monomials or something, the kind of task of sampling from it can be computationally intractable in some precise sense that we'll get back to in some number of slides. On the other hand, score matching is, in fact, not just efficient to calculate here. It's actually just minimizing a quadratic, because you see when you look at log p theta here, it's linear in theta. So the objective basically has just like squares of this quantity. So it's just minimizing a quadratic. So not only is it actually efficient to optimize it, it even has a closed form. Doesn't really matter what this closed form is, but you can just kind of calculate some expression in closed form from the training data. And so it's kind of very efficient to calculate it. So we kind of already have this tension that algorithmically it seems hard to do kind of maximum likelihood optimization with like a gradient-based method, but score matching is efficient. So let's kind of now see how the statistical behavior is going to be of score matching. So I'm going to focus on the asymptotic case here. We do have some non-asymptotic results in the paper. If you want to ask me about it afterwards, we can. But these kind of are the cleanest results. So just to introduce some notation, I'm going to call sigma x the covariance matrix of some random variable x. It turns out that for exponential families, the following statements are true. So maximum likelihood is asymptotically normal, which just means that if you look at the kind of appropriately scaled difference between theta hat MLE and theta star, it's going to converge to mean zero Gaussian with some covariance matrix. The covariance matrix here is just the inverse Fisher information matrix. It turns out that score matching is also asymptotically normal. So again, if you scale it appropriately, it converges to mean zero Gaussian with some other covariance matrix, which I'm calling gamma SM. It's an uglier expression that looks something like this. You don't really actually have to track very much, other than the kind of the only thing that I want you to notice is if you look at this expression for gamma SM, it's a product of three matrices. One matrix that looks like expectation JF transpose inverse. J is a Jacobian. So if you look at this matrix, and if you look at gamma MLE, they look kind of very similar up to the fact that there's an extra derivative. So somehow sigma f is expectation FF transpose. This is expectation JF transpose. So they're kind of similar up to one derivative. And the way that you kind of calculate this expression is like completely standard. If you just really have any kind of estimator that's the minimizer of some kind of empirical loss capital L of theta, which is the expectation of some little losses little L of theta, there's some expression that you can write down for the kind of asymptotic covariance matrix. You just kind of plug in the appropriate expressions, and that's how you get this expression for gamma SM. There's nothing kind of magical going on there. So if we want to compare now the statistical efficiency of score matching, what we want to do is we want to somehow see how much bigger the matrix gamma SM is compared to the matrix gamma MLE.
I know that this is not the focus, but I'm just curious. Can you comment on whether these regularity conditions are the same? So you have the same, for like an exponential family, the same conditions that we require for this?
I don't know if the minimal assumptions are the same for both of them. So for exponential families, if, for example, gamma MLE is non-singular, you basically have asymptotic efficiency for score matching. It's possible that there's like some kind of corner cases where one of them is asymptotically normal, but the other isn't. I don't know offhand. For the theory, we just assume enough regularity that both of these guys kind of exist and are well defined, because we just want to kind of get the rates for them. Yeah, good question. Okay. Good. So unfortunately, a couple more technical quantities that I have to define. So I'm going to define what's called the restricted Poincare constant, which I guess first requires me to define what's called the Poincare constant. So the Poincare constant is the following quantity. It's the smallest constant CP. Actually, sorry. First of all, this is a quantity defined for some distribution, let's call it little p. And it's the smallest constant such that for any smooth function f, you can upper bound the variance of that function by this constant times the expectation of the gradient of f. If you've not seen this before, I believe that this looks very strange, and it just sort of looks like kind of very unparsable. It turns out that this quantity is related to the spectral gap of what's called the generator of Langevin diffusion. If you're more comfortable with discrete Markov chains, this is some continuous analog of the Laplacian. If you're doing like a random walk over a graph, the important thing is that this constant characterizes the mixing time of the chain that we're interested in, of Langevin dynamics, in some notion of distributional distance. It turns out that chi-squared is the right notion. Okay, so what is the restricted Poincare constant? It's the same quantity, but rather than sort of looking at the smallest constant over all functions f, you look only at functions f that have some restricted form. So they're functions which are linear in the sufficient statistics. So of course, because you're looking at a smaller set of functions, certainly this constant is smaller. How much smaller? I'll show you some examples where it can be much smaller. Questions about these two? Yes?
For every type of distribution, I know it goes for like Gaussian or symmetric Bernoulli, but isn't that a bit restricted? Like, does it work for every type of distribution?
Oh, you're saying like how restricted is it to even assume that it's finite or something? There certainly are distributions for which it's not finite, like that I'm not going to be interested in those distributions. That's just it being finite is not a very big restriction. Okay. So just to kind of sanity check, so it turns out that if you look at these kind of, I guess, like cartoon boogeymen that we were looking at, so like let's say a bimodal distribution with faraway modes, you can kind of do a calculation and, for example, calculate the Poincare constant of a mixture of two Gaussians with means at -a and a, and see that it's sort of exponential in the distance between the means, so exponential in a squared. So what this tells you is that this is somehow like a strict generalization of this kind of toy example of like very multimodal distributions. Okay. So now I finally have enough machinery so I can tell you what the theorem looks like. So the theorem basically says the following. So I'm trying to upper bound the norm of the matrix gamma SM, and I can upper bound it as follows. So it's basically, it's upper bounded by twice times the restricted Poincare constant squared times gamma MLE operator norm squared. So this is basically the term that kind of characterizes the efficiency of MLE. And then times what I called like a nuisance term, so basically some quantity that has something to do with like the norms of the parameter theta and some like expectations of derivatives of f. So somehow how nice and smooth the sufficient statistics are. So this is the theorem statement. I'll do a bunch of remarks around this, but maybe before I do that, are there any questions about the statement? It's the Jacobian of f, so it's the derivative of f. Yeah. Yeah.
For normal or for any distribution?
Oh no, this is for any exponential family with sufficient statistics f. Yeah. So,
Why is the operator norm the right measure of?
So technically, you want the trace because if you look at the expectation of theta star minus theta whatever, but if you have an upper bound on the operator norm, you can just like upper bound the trace by losing a factor of dimension or something. So.
So
You said the control constant controls the mixing time.
Correct.
Is it also the converse true? I mean, is it tight, or I mean, are you actually getting here the mixing time, or only in terms of something that does mixing time?
It depends what you're willing to assume on. Depends how worst case you want to be with respect to the starting distribution. If you want to be worst case with respect to the starting distribution, then yes, it's a kind of if and only if. If you're allowed to do some warm starts, then no. There's another question somewhere over there. Yeah. That's a very good question. So maybe give me like one slide when I show you what's the idea of the proof. So I think that's an artifact of the proof. I don't think that should be real, but at least I'll tell you where it's coming from. If I don't, remind me. Okay, good. So let me sort of make some remarks. So maybe just like some super loose, like intuition. This is not how the proof works, but maybe why would you expect these kind of terms to appear on the right-hand side? So okay, somehow like maybe here's one way in which you could think. Well, I have the score. I'm trying to extrapolate the score into a distribution. So one way to do it is by running like Langevin, running this Markov chain. And what I could kind of imagine is that the longer I run this chain for, the more the kind of the error accumulates. So maybe there should be something that shows up in kind of in the right-hand side that tracks kind of this error of accumulations. You can kind of think of it as some stochastic, fundamental theorem of calculus. And then I need something that sort of something that kind of looks like a kind of complexity term that standardly shows up in generalization. So here that's being played by the smoothness. So this is maybe some like super loose intuition why something like smoothness and something like a quantity having something to do with like mixing time should show up. As I said, this is not how the proof works. It's actually much kind of crisper, and I'll show you how the proof works. So a couple more other remarks. So in some sense, like some dependence on both something like a Poincare constant and something like smoothness is required. This is purely qualitative. I'll kind of give a hint of what the lower bound looks like, but probably quantitatively, many things are not tight in this expression. I guess maybe, Siva, I preempted your question. And from this, if you sort of want to extract quantity, maybe this kind of goes to Samori's question. If you want to extract something like, error bounds on, let's say, how much different theta hat SM is from theta star compared to theta hat MLE from theta star, you can very easily just kind of extract something like, a bound on the error of theta hat SM by kind of like, just going through some standard machinery like, Markov's inequality. So that's basically what I want to say about the statement. Sorry, tell me. Yeah.
Regarding the classical results about optimality,
yeah.
They presumably say the trace is the smallest amongst all matrices that you can get there, right? Do they say more? Do they say it's like the smallest matrix you can get in PhD order or something like that?
Yeah, yeah.
So a priori, it's clear that this matrix is bigger than that matrix in PhD order.
Okay, good. So let me tell you the main idea in the proof. So let me remind you, this was the expression for gamma SM. And so it basically turns out that if you look at this expression, there's two matrices involved. There's this expectation JF transpose inverse matrix that shows up on the kind of at the front and at the end of this expression. And then this covariance matrix of this kind of quantity down below. It turns out that this sort of middle matrix is very easy to upper bound by just sort of triangle inequality. So this is like a covariance of a sum of two terms. You can kind of do triangle inequality to upper bound it by the sum of the covariances of the kind of individual terms. And this is kind of where you get the smoothness term from. The kind of term that seems a priori unclear how to bound is these like matrices that involve derivatives of f. And it seems a priori unclear because the thing that you have control over, because it appears in maximum likelihood, is like the same matrix without the derivative. So somehow the worry is like, could introducing extra derivatives make this matrix very singular? And the key lemma is that no. So you can basically upper bound this matrix. So you can upper bound expectation JF transpose inverse by the restricted Poincare constant times the inverse Fisher information matrix. Okay, so let me show you where kind of how this lemma works. So here's what we're going to do. I'm going to take some test vector W. I'm going to evaluate the left-hand side without the inverse in this direction W. So I'm going to look at W inner product expectation JF transpose inner product W. By kind of linearity of expectation, this expression is just the same as the expectation of the gradient of W inner product f of x. And now what do I do?
Poincare inequality?
Yeah, so this is the expectation of a gradient of something that's linear in the sufficient statistics. So by the restricted Poincare inequality, I can lower bound this by 1 over the Poincare constant times the variance of the thing inside, W in a product f of x. This is nothing but the kind of evaluation of the quadratic form corresponding to sigma f in the direction of W. And then you basically just apply monotonicity v inverses, and then that gives you the key lemma. And that's basically the main ingredient in the proof. Now, why was there an extra square? The extra square is because somehow what happens in maximum likelihood is like you have 3 matrices, and it turns out in maximum likelihood the middle matrix is the same as the outside matrices, so there's a cancellation. This expression sort of like, has 2 inverses and 1 non-inverse, so you expect some cancellation to happen. Here, I just don't know how to cancel anything. I just like upper bound each of the terms individually, and so I kind of pick up the outside matrices twice, so I get like the sigma f matrix twice, which is why I get a square in the kind of term that has theta MLE in it. That's basically the reason it's off by a square. I think this is an artifact to proof, but I'm not sure. Okay, good. So the lower bounds are a little bit technical, but let me give you just like a hint of what they look like, because it's going to be a good sort of motivation for the next part. So, oh, sorry, go ahead. Yeah. Yeah.
So this lemma you show the division of the upper bound, because this matrix appears on the left-hand side and right-hand side. And I don't think we can pass this lemma to bound the gamma as a derivative. No,
It's just submultiplicativity of operator norm, right? I'm upper bounding the like operator norms. No, I'm just gonna upper bound like the operator norm of the site, and then it's just like submultiplicative operator norm. Yeah, but a good question. Yeah.
How does the upper bound look in simple cases where you can calculate things like if you're estimating the location parameter for a Gaussian?
So a Gaussian is actually not interesting because the score matching loss is the same as maximum likelihood. If you do something like a mixture of Gaussians, it's sort of no longer explicit, so it's unclear.
Yeah.
I don't know like what's a simple case to kind of explicitly evaluate it. It's kind of like very interpretable, if you like.
But the Gaussian is kind of a trivial case, right?
Oh, but the 2 losses just collapse to each other, right?
Right, but your inequality has very different things on both sides.
Sure, yeah, that you're right. Like it's not going to be tight at all, like for the Gaussian case, yeah. I think even in general, like even for arbitrary distributions, I suspect the bound is not tight. Yeah. Go ahead.
How small the restricted
Yes. Yes, in some specific cases I will, yes. Okay, good. So here's sort of roughly what the lower bounds look like. So suppose I take some p theta, which is in some exponential family, and suppose that it has a large unrestricted Poincare constant. That doesn't necessarily mean that it has a large restricted Poincare constant. But what it does turn out is that you can view p theta as a subset of a kind of augmented exponential family, where you add some sufficient statistics f, like let's say f2, and then you just think of this like the kind of the theta in like the theta 2 in kind of in front of that f2 as just being 0. This is trivial, of course. But it turns out that if you kind of pick this f2 in some careful way, in this kind of augmented family, the restricted Poincare constant gets to be big, and then score matching performs badly in the following way. You can look at the kind of evaluation of the quadratic form in suitably chosen directions for gamma Sn and for gamma MLE, and you can kind of prove that this quantity can be lower bounded by something that roughly is kind of lower bounded by what's called the isoperimetric constant of the distribution. So this is some quantity that characterizes kind of how whether there are sparse cuts in the distribution or not. If you kind of have never seen it before, it's very closely related to the Poincare constant, but not the entire, like I'm not going to give you a formal statement here, just like let's leave it be that there are 2 kind of very related quantities. And in fact, the way that you produce this f2 to add, so you make the kind of the lower bound tight in the sense is that this kind of added sufficient statistic is sort of like a smoothed indicator of a sparse cut in the distribution. So I guess in a nutshell, what it says is you can kind of make this bound qualitatively tight if you replace Poincare constant with a kind of with the isoperimetric constant. If you kind of think of the distribution as lying in an augmented exponential family, which is kind of rich enough to have some like some member in the exponential family that approximates something like a sparse cut. Good. And so it turns out if you just like track the calculation that I gave you, turns out that the only thing that I really needed to assume out of exponential families here is that the estimators are asymptotically normal. If you are in fact willing to just assume that they're asymptotically normal, pretty much the same calculation works just like it did, and you can kind of prove the same result. The only thing is now you have to like take in the asymptotic normality as an assumption. In the exponential family case, you just sort of like you can prove it yourself. Like it doesn't have to be an added assumption. But otherwise, the kind of result still holds, where you just sort of appropriately modify the terms in the kind of in the smoothness part of the bound. Okay, so I guess I've like whet your appetite enough. So I said that this restricted Poincare constant can be much smaller. So let me sort of show you cases where it can be much smaller, and in fact, like a pretty kind of general class of distributions where you can kind of effectively leverage this. Here's a kind of simple simulation that you can do. So you can look at a distribution that is actually multimodal. It kind of looks like a mixture of two Gaussians, even though it's not. So you can kind of look at this this sort of like distribution that looks like it lies in some exponential family where the sufficient statistics are monomials of degree up to 4 or something. And if you kind of plot it, it looks very similar to a mixture of two Gaussians with like means at -a and a. And now you can try to play the following game. You can try to treat this distribution as lying in two different exponential. Oh, sorry, go ahead.
Couple of slides here. For the lower bound, yeah. Why can't you directly just add the large eigenvector of the unrestricted Poincare constant into your exponential family to get the lower bound? Why do you have to go to the cut?
Well, I mean, the sort of sigma f and all of the other matrices depend on your choice of f. So if you have like an extra f, then the bounds basically depend on your choice of f. Like this is basically like if you take like a very low complexity like function or something, you can trivially treat it as being a part of a larger complexity family, but then your kind of generalization bound will suffer whichever family you're treating it to be a part of. So, yeah. Any other questions while I'm back on these slides? Go ahead.
Quick question on the formula.
Yeah.
What are the units of the left and the right side? Like just like, are they the same units for the formula? Like if you scale f here on the left and the right.
Yeah. So this bound is not scale invariant. I think I also don't know if that's a kind of artifact of the proof. As written, the bound is not scale invariant. Yeah. Talk to me offline. I have thoughts on this, but like it'll take us a little bit too far afield. Yeah. Okay, so what you can do is you can play the following kind of game where you treat this distribution as being a member of two different exponential families. Doesn't really matter what these exponential families are. Just in one of them, I'm going to have one of the kind of sufficient statistics look like something which has this ERF function. So this ERF function looks something like this. So it basically looks like a cut in this distribution. So I'm going to kind of treat it as a member of some family, one coordinate of which can kind of approximate cuts in this distribution. And as you can see, in this case, if I look at the kind of parameter estimation error for score matching and MLE, the kind of larger and larger I make the A, so the larger and larger I make the distance between the modes, the worse and worse score matching gets compared to MLE. On the other hand, if I choose the kind of exponential family such that it doesn't have this kind of sufficient statistic that approximates a cut, you can see that even if I make A larger and larger, sort of score matching and MLE are kind of not too far away from each other. And in fact, increasing A doesn't seem to do much to the kind of to the parameter error. So it turns out that this is a kind of general phenomenon. So here's what we can show. If you look at an exponential family where the sufficient statistics consist of all, let's say, monomials of degree up to some little d, and maybe you place some L infinity bound on the parameters theta. And then there's some kind of base measure h of x, which I'm showing in light gray because it doesn't matter too much. It's basically something to make sure that this is a kind of proper distribution. And sort of the theorem is that in this case, you're you got a good bargain. So basically, score matching is going to be not too much worse than maximum likelihood. So it's going to be only polynomially worse if you think of little d as being a constant. So it's going to be something like O of little nb to the poly of d factor worse than MLE. And moreover, because in this case, the score matching estimator is just minimizing a quadratic, it's a computationally efficient algorithm to do so. On the other hand, it is actually intractable to optimize MLE using a gradient-based method. And in fact, what we can show is that implementing a kind of a first-order oracle is impossible unless NP is equal to RP. So this result is somehow morally similar to some results that actually predate this by some number of years in the case of discrete distributions for Ising models. So there's a kind of nice line of work that started with Bressler and then continued into a paper by Wolfray et al., which showed that there are kind of classes of Ising models, and particularly Ising models where the degree is bounded, such that you can kind of learn them in a computationally efficient manner with a close to kind of statistically optimal rate. But maximum likelihood seems intractable to actually optimize. And in fact, the algorithm that these papers use is something called interaction screening, which is in some ways a kind of close relative of pseudo likelihood, which is itself some kind of discrete analog of score matching. If you don't really know what it is, don't worry about it. In fact, I'll go back to it briefly towards the end. But morally, these results are kind of a continuous analog of some kind of developments that happened like several years ago in the discrete world. Yeah.
So the hardness you're showing is always hardness in the sampling that's required in order to calculate it.
Here's the more formal version. So the hardness is the following. So the hardness is that suppose I ask that you implement a first-order oracle, so an oracle that at any given theta can calculate the gradient of, let's say, the maximum likelihood at particular theta. If you want an oracle like this, it's impossible to implement unless NP is equal to RP. That makes sense? So it's a kind of worst case result in the sense that the oracle is required to, at any theta, output the gradient of the likelihood at that theta. So it's, by virtue of the fact that it's a computational intractability result, something is going to be worst case. In that sense, it's worst case. But this is sort of making formal the fact that if you're expecting a first order oracle that works anywhere, you should not expect that.
Yeah, I may have missed the setup a little bit, transitioning.
Yeah.
What's the likelihood model?
Data is generated from p theta star for some choice of theta star, and the distribution p theta star is like proportional to exponential of theta star in a product f of x, where f is sort of the list of all of the monomials of some degree up to little d.
So this is just a statement about the normalizing constant being hard to compute, I guess?
Somewhere underneath the hood for this hardness result, yes. It's relying on the fact that some basically evaluating the gradient oracle implicitly requires some kind of partition function, and then the partition function is NP hard to calculate, even if the sufficient statistics are low degree monomials.
I'm a bit surprised that the hardness assumption here is NP not equal to RP as opposed to some kind of counting class, like Sharpie hardness, because
it's because it's okay. I'm giving you the version for if you want the constant additive error version, then it has to be about NP rather than about Sharpie. If it was exact implementation of the oracle, then you could even prove Sharpie hardness. But I'm also allowing slack here, so the hardness even works if you allow slack. But fair point. Yeah. All right, good. So I'm not going to say very much about the proof. This is, again, sort of the way that the main kind of lemma is proving a restricted Poincare constant. It looks something like this. You can basically upper bound the variance in terms of something like the condition number of the Fisher information matrix. And the only thing that I'm going to say is that the reason why kind of polynomials are useful to make this proof work is that somehow they have this downward closeness property. So if you take an f, which is a polynomial, and you take gradients of it, it's going to be also a polynomial of degree lower than f. So this is somehow useful in a bunch of the calculations. And then you kind of bound all of these terms in green, and that's kind of how you get to the statement of the theorem in the previous slide. Okay. Final part, not final part, but part 3. So here's somehow now something that might bother you. what I showed you is like some kind of connection between the mixing time of Langevin and the statistical efficiency of the score matching estimator. And somehow, like, you might think, like, what's so special about Langevin? Like, why does it appear in these bounds? Like, why not some other kind of Markov chain? And the result, and sort of like the answer is somehow nothing. So basically, what we show in this paper is that you can kind of build a dictionary in which what you get to do is you get to give me a fast mixing diffusion, and then I will give you a score-like loss with behavior that's kind of characterized by the mixing time of this diffusion. So the kind of result roughly says that if for kind of all sufficiently nice time homogeneous diffusions, you can basically cook up a corresponding score-like loss such that the kind of error of the estimator that corresponds to this loss can be kind of upper bounded in terms of the efficiency of maximum likelihood and the mixing time of this particular diffusion. Let me show you how this works. Sorry, maybe I'll skip this for now. Let me show you how this works. So first of all, what are the kind of losses that we're going to be looking at? So the losses are something which is called a generalized score matching loss. So the idea is the following. What you're going to try to fit is for some choice of linear operator, you're going to try to fit OP divided by P. So for instance, if O is just the gradient of P divided by P is gradient of log P, so you get back standard score matching. For other choices of O, this is going to be some other loss. And then the theorem basically says the following. If you pick this O to be something like the square root of the generator of your favorite choice of diffusion, you will get exactly the same kind of bound that you got before, but now you will get the Poincare constant that corresponds to the Dirichlet form for this diffusion. So basically, you will suffer the mixing time of this particular diffusion. So why is this nice? This is nice because by and large, understanding statistical efficiency of losses is a harder task than it is to come up with fast mixing Markov chains. But this gives you a dictionary so that you can kind of like use all the tricks in the book that we know for speeding up Markov chains and get statistically better behaved losses. So for instance, one way that we know how to speed up kind of Markov chains is by preconditioning. So for instance, what you could do is you could take something like Langevin. You could precondition it by some matrix-valued function d, and then kind of adjust it by some appropriate drift factor gamma so that the stationary distribution is preserved. And if you kind of churn through this calculation and you look at what the corresponding generalized score loss is, lo and behold, it's exactly the kind of standard score loss, but preconditioned by the square root of the preconditioner that you chose in the Markov chain. So kind of preconditioning of the Markov chain corresponds to some kind of preconditioning in the loss, and the statistical efficiency of the loss in turn can be kind of characterized by the mixing time of the diffusion that you picked. So another kind of trick in the book that we have for speeding up Markov chains is lifting the chain. And actually lifting the chain, it'll turn out has like quite a close connection to kind of strategies that people have used with these score-like losses to improve them in practice. So in fact, what you typically do when you try to kind of train a score-based model is you don't just try to fit the score of your basic of your distribution, but you try to kind of convolve it with a whole bunch of different levels of noise sigma I, and then you try to simultaneously kind of fit the scores of all of these convolved versions of the distribution. And sort of the loss is then some kind of weighted sum of how well you fit the score at the different kind of amounts of noise. The intuition behind this is supposed to be that if you add a lot more noise to some kind of multimodal distribution, it's going to start to look more and more unimodal. So it should be easier to kind of fit the score, and somehow like the fitting at the higher levels of noise should also help you fit the score at lower levels of noise. It turns out that this has a buddy in kind of in sort of sampling world. The buddy is like tempering or lifting strategies, where what you do is the following. You are kind of in a situation where sampling from some distribution P of x you think is slow. But what you can do is you can try to kind of sample from some distribution where there's an added kind of temperature, or in this case, convolution parameter beta. And the sort of joint distribution here is sort of the following. You basically pick some temperature beta according to some kind of weighting of the relative, some relative weighting of the temperatures R of beta. And then you conditionally sample from the distribution with like, convolution amount beta. In sort of tempering, you would think of this beta as a kind of temperature parameter. So you would scale the distribution by, some factor depending on beta. Here, we think of it as a kind of sort of convolution factor, so we kind of add some amount of noise. And it turns out that if you write down the generalized score loss that corresponds to Langevin, but on this joint distribution, it will look eerily like the loss that I showed you before. So it will look like the following. There'll be a term on this first line, which is a weighted sum of how well you fit the scores, where the weighting is given by this quantity R of beta. And then plus some other term that doesn't show up in the typical kind of score losses that people use, which is kind of like a higher order term of how well you fit the score. So basically, it's like it's some term kind of describing how well the traces of the Hessians are fit. Don't ask me how well it works if you add this term back empirically. It's kind of impossible to train this. We tried it for a very long time. The training becomes a lot more unstable, so it's very hard to actually fit. But anyway, this sort of gives you now some inkling for trying to understand why these kind of tempering strategies help. So here's kind of one specific case where they help. So suppose that you have a distribution that's multimodal. So if you kind of look at the standard Poincare constant, it'll be very bad. On the other hand, suppose that it's a kind of a mixture of Gaussians, and let's make some kind of structural assumption. So maybe it's a mixture of Gaussians where each of the components have the same covariance. Then it turns out that sort of running Langevin on this lifted change that I showed you before is much faster than basic Langevin. It turns out that the mixing time is basically Pauli in all of the kind of relevant parameters. So it's Pauli in the dimension, the kind of diameter of the action, so how large the means are, and the minimum and maximum eigenvalues. In fact, it turns out that there's not even a dependence on the number of components. And then if you kind of plug this back in the kind of generalization machinery, what you can show is that if the data distribution is in fact a mixture of Gaussians with, like, let's say some known covariance and weights, and you just try to estimate the means in kind of the natural parameterization where the thetas that you're estimating are just the unknown means, then you can basically show that the sort of generalized score loss that I showed you in the previous slide is only worse off compared to maximum likelihood by like a factor which is polynomial in all of these relevant quantities, whereas the basic score loss would of course be very bad, because even for a mixture of two Gaussians, the Poincare constant is just very big. So this is sort of a way to explain the statistical benefits of these annealed losses by kind of like relating them to the mixing time of the tempering chain that I showed you. Not going to say very much about the proof because it's kind of fairly technical, but maybe for the experts, the main kind of thing that you have to show is in this kind of mixture of Gaussian case, you have to show that this kind of lifted chain that I showed you has a kind of fast mixing, and the way the sort of the main ingredient is that we use is what are called decomposition theorems. Pictorially, what I'm showing you here is you can kind of imagine the joint distribution at different temperatures beta, and this is kind of supposed to be the x, and this is supposed to be the beta, and these kind of proofs proceed by basically somehow showing that there are no bottlenecks if you go kind of vertically. So if you look at slices where you look at the kind of different temperatures beta, but like a chunk in kind of x space, there's no kind of bottleneck there. And kind of also if you look horizontally, there's also no bottlenecks like that. And so you kind of stitch these two things together, and that's kind of how you prove the mixing time bound. Okay. Next part. So somehow everything that I talked about here is about the continuous case. However, in some ways, there's something a little bit unsatisfying, which is that for the continuous case, diffusion models kind of already work very well. It turns out that the picture is a little bit more murky in the discrete case. Let me just give you a little bit of kind of motivation. So again, unless you're living under a rock, you know that sort of the dominant paradigm for how people do language modeling these days is via the kind of autoregressively parameterized paradigm, which is to say that you parameterize some joint distribution by kind of some parametric form, which can give you probabilities for xi given the previous context x1 through xi minus 1. So for all its benefits, like there are some pain points with this paradigm. Maybe the biggest kind of issue is that it's inherently sequential. So if you're trying to generate n tokens, you basically can't generate token I until you've generated tokens 1 through I minus 1. So you can't really efficiently parallelize it, which you would like to do, because one of the things that GPUs do well is parallelism. So that's kind of one pain point. And there's a kind of variety of works that are somehow trying to latch onto some other limitations of kind of having an autoregressively parameterized distribution. Some of these works are older. There's also kind of some very recent resurgence of this kind of line of work. In fact, one of these authors will show up in the second workshops if you want to come and listen to it. So the kind of one alternative that's proposed here as a kind of non-autoregressive way to generate a sequence is the following. So you might think about the following kind of iterative refinement process. you generate the entire sequence fully randomly at first. So you start with just pure noise, and pure noise could be either random tokens or all like mass tokens. And then what you try to do is you iteratively try to refine your guess. So you're going to have some procedure that basically in one parallelizable forward pass tries to somehow update multiple of these positions simultaneously. And the reason why this is kind of lends itself better to kind of parallelism is that if each of these steps of refinement is somehow implemented by a transformer, transformers are typically kind of pretty friendly towards parallelism. And which means that if you don't have to take too many steps of refinement, then sort of like you have a parallel efficient algorithm. So how does this get operationalized? This is, in fact, somehow quite close to BERT, which is typically not thought of as a generative model. It's thought of as a kind of way to learn features. But the idea is the following. So you're going to somehow train a model that, given some subset S and some value for the tokens outside of S, so so the value of the tokens in XS bar, can spit out a probability distribution for the rest of the tokens. So for instance, maybe you have a sentence like, Andrew Carnegie famously said, "My heart isn't the work," and then you mask some words. So Andrew Carnegie famously masked, "My heart isn't the mask," and then the model can give you some predictions for what these mask tokens are supposed to be. OK, so far so good. This is probably familiar to most of us. This is how BERT works. So how do you use this to produce a generative model? Well, it's very simple. If you have something that can give you conditional probabilities, there's a natural Markov chain you can run, which is just a Gibbs sampler. What's a Gibbs sampler? So you kind of repeat the following process. If your current state is x1 through x1, what you're going to do is, like, first you're going to pick some set S to randomize. There's many ways to do this. Maybe you just sort of pick a random set of a certain size. Maybe in a round-robin fashion, just go through all case-size subsets. Could be anything. And then you resample the components in S condition on the values of everything else. This is kind of the re-randomization step. Then you update your state to be the new values for the coordinates in S. Everything else stays the same, and then you repeat. It's like coordinate ascent, but in a sort of randomized, like in a Markov chain form. So what we show in this paper is that there's a kind of analogous dictionary you can cook up to what I showed you in the continuous case. So it turns out that you can quantify the sample efficiency of these mass language modeling like losses via the mixing time of some corresponding Markov chain, in this case, a Gibbs sampler. So what is kind of the degree of freedom? The degree of freedom in the kind of mass language modeling losses is how you pick the distribution over the mass positions. And it turns out that the way that translates to the kind of Markov chain is how do you pick the kind of the choice of set S when you're picking which set to randomize. So again, there's like a kind of translation that tells you, like, if you have a fast mixing Gibbs sampler with a particular choice of distribution for the sets S to re-randomize, there's a corresponding mass language modeling loss that you can cook up with. The proof is basically the same. It's more or less like you kind of relate you write down the expression for the asymptotic covariance of maximum likelihood. You relate it to the asymptotic covariance of the corresponding mass language modeling loss, and then you lose a factor of Poincare inequality. It's a kind of computationally, it's very similar to the proof that I showed you before. OK, so now let me maybe use the last 8 or 9 minutes to pontificate a little bit. So I'm going to try to kind of give you the outlook at sort of various time scales, and I'll try to zoom out a little bit and talk maybe about generative models more generally beyond score losses. Maybe kind of most immediately, just sort of nearest to what I kind of told you about, this particular kind of work for me personally was motivated by the fact that in some ways, diffusion models in the continuous case already work pretty well. For whatever reason, it doesn't seem like this kind of machinery works all that well in the discrete case. And one of the kind of hopes that I have from this line of work is that we can kind of use theory as an inspiration to give better losses, for instance, based on some choice of dependent Gibbs samplers. We know plenty of kind of cases where the basic Gibbs sampling is kind of very slow, but then you can kind of cook up better samplers where the kind of coordinates that you update are chosen in some kind of smarter way. If you know the buzzwords, like a particular example here is Swenson-Wang, and this kind of machinery allows you to translate them into losses. In some ways, what I showed you in this paper is kind of like an analog of what the kind of very first result that I showed you with Fred and Xander was for the continuous case. So again, it'd be interesting if we can understand annealed variants of discrete diffusion models, which is another kind of topic that people have tried to empirically work on quite a bit, starting with this paper by Austin et al. In 21. And the kind of lens I used in this talk was predominantly a statistical one. There's plenty of other ways in which we think that score-based models have benefits. So, for instance, another kind of alternate lens is an optimization lens. So perhaps, like, for some reason, there's some more benign landscapes that we get when we're trying to do score-based approaches. There's some nascent work in this line, but pretty much anything that you like, any sort of flavor of question you ask here is almost certainly open. So this is kind of maybe most myopic. So zooming out a little bit, in some ways, the sort of the kind of several works that I showed you before are in some ways about understanding limitations of the kind of particular choice of generative modeling paradigm. So the kind of choice of loss and so on and so forth. And this is kind of one type of question that you can ask. Alas, the kind of pipeline for generative modeling nowadays is kind of much more complicated and involves a whole bunch of other moving parts. So for instance, it's pretty common to kind of, on top of the pre-trained model, do various types of modifications to the algorithm used to draw samples, so to the inference algorithm. So for instance, for efficiency reasons, one often uses kind of numerical acceleration schemas. If the model is like a kind of diffusion-based type of model where there's some discretization of a stochastic process, and then you kind of can try to use accelerated sort of discretizers. There's a variety of techniques that try to sort of get a better parallel efficiency by leveraging what are called parallel decoding techniques. So these are kind of various fixed point solvers like Jacobi decoding, Picard iterations, and so on and so forth. And then there's also kind of a variety of training-based modifications to the model. Sometimes they're for quality, sometimes they're for efficiency. Perhaps the thing that we all know is like in various types of fine-tuning strategies. They could be just normal fine-tuning, instruction tuning, or tuning on preference data collected by humans via RLHF. Oftentimes what you do is you take the pre-trained model and then you try to make it smaller by distilling it to a smaller model. And finally, there's oftentimes strategies where you draft another kind of what is called a suggestion model that tries to, in some ways, kind of generate in a quick fashion guesses for the bigger model, and then the bigger model just needs to somehow verify them. In all of these cases, it's oftentimes not, first of all, it's not clear how much you can fix up, in some sense, faults in the original model by these post-training strategies. It's actually most of the time not even clear how to formally phrase this question. So in some ways, as a kind of goal for the program, even figuring out appropriate ways to phrase these questions is a kind of open question on its own. And then maybe kind of zooming out even further, I think in some ways, what us theorists have been good at with respect to kind of understanding generative modeling strategies is we've been kind of fairly good at analyzing specific generative modeling paradigms, losses, training methods. This could basically involve both things like understanding what I would call kind of generic properties. So things like, is the class that we're using a universal approximator? So sort of things that if they didn't hold, probably you would want to fix up the class that you're using. So we have results like this for a variety of kind of push-forward models, maybe GANs, variational autoencoders, and so on and so forth. We also have statistical rates for pretty much all of these models. And again, most of the time, what these results will say is that, generative model class such and so is minimax optimal. And again, if that doesn't happen, there probably something went awry because these are kind of worst-case results. And if you're not minimax optimal, there are other more classical methods that are minimax optimal. So probably something went awry somewhere. We've also been, I think, fairly good at sort of analyzing specific failure modes. In many cases, diagnosing them. In some cases, even mitigate them off, again, specific model classes. So for instance, I am old enough that during my PhD, I thought quite a bit about mode collapse and sort of generalization in GANs. There's quite a bit of work in kind of around the early 2000s around something called posterior collapse in variational autoencoders. There's a variety, quite a bit of work around diagnosing and mitigating conditioning and normalizing flows. And nowadays, there's quite a bit of work around understanding error propagation in diffusion, numerical error propagation in diffusion models. That's something I hinted at in the beginning. So somehow what we're very good at is once somebody hands us a paradigm, we can kind of understand specific faults with it. What we have not been very good at is to sort of provide any kind of separations between different types of generative modeling paradigms or losses and training methods, and in particular, a kind of theory that somehow usefully guides the next generation of generative models. Perhaps we agree on this, but just in case not, here's some questions to ask yourself that I think to which I think the answers are fairly clear. So for instance, if in 2015 somebody asked you, like, our diffusion model is going to be the generative model class that's going to win out in 2024, I doubt anyone would have said yes. And there's no theory, there's no heuristic argument to suggest this. Nowadays, the situation isn't that much more different. So there's plentiful debates nowadays about, like, whether, when, or why autoregressive models in text are superior or diffusion models in images are superior. It's not actually clear. It's not actually clear we know how to even formulate this question. But certainly, if you go, like, on Twitter or X nowadays, there's plenty of debates. But then again, there are plenty of these debates for every past model class. So when GANs came around, there are plenty of arguments for why they're definitely better than VAs, and they're definitely there to stay, and there will definitely be no other generative model. So the situation hasn't changed that much. And in some ways, I think this is like a call to arms for theorists, because trial and error, which was the dominant strategy for how to figure out what to do next, was basically the de facto way to do things when models were smaller. Now, like, at the current size of models and the current amount of data, it's simply not feasible to kind of retrain a model at the size of Midjourney or DALL-E with, like, 3 or 5 different architectures. Just it's neither temporally nor monetarily feasible. So in some ways, the reason why this is a challenging task is clear to all of us. Both the kind of the architectures, the models, the kind of pipelines, as well as the data have gotten very, very complicated, which makes things kind of challenging for theory, but also kind of exciting. And in some ways, I think what we need to think about is, like, what are reasonable abstractions, kind of parts of the analysis to oracle away, sandboxes to study, such that they toe the line between being A, clean enough that we can do mathematical analysis, and B, they're sort of like useful enough in terms of modeling that they kind of facilitate both understanding of relevant phenomena and ways that we can intervene on training, meaning we can improve the ways that people train models currently. And just to be on a very positive note, I think we have a great crowd of people here, and I don't think there's any better place to do this than at Simons. So, looking forward to a great semester, and that's all I have to say. Yep.
Yeah, regarding the irreversible dynamics, like the and the systematic or the dynamic. Can you talk about any results or measure results related to this dynamic?
Sorry, I'm not sure where the irreversibility comes from. Yeah.
Yeah, I mean, irreversibility just means you have the systematic part in your
Yeah.
So are you aware of any results related to this dynamic?
Not off the top of my head, no.
Thank Andrej again.